Another interesting set of stars that you guys need to know about are variable stars. These are stars that can change their brightness. There's a couple different reasons that stars are going to change their brightness. The first is what's known as a pulsating variable. And a pulsating variable is basically a star that's going to get bright and dim. They usually do this over a very regular period of time. And if they do that, we call them a Cepheid variable star. The reason this happens is because of what's going on in its core. It's doing fusion, and as fusion is pushing out, it's going to cause those outer layers of the star to expand. When that happens, there's less pressure pushing down on the core, and so fusion starts to slow down. And as fusion slows down and it's shrinking, it'll shrink and push down more, which will then speed fusion up. And then the fusion will speed up, push out more, and the star will expand where there's less pressure, so fusion slows down, and the star will start to shrink. And it does that repeatedly, sometimes over a course of a few hours, a few days, a few months, a couple years. As it is expanding, it's going to have more surface area. If it has more surface area, there's more area for light to escape that star. And as it gets bigger, it's going to seem brighter to us. When it shrinks, even if it's roughly the same temperature, because it is a smaller surface area, not as much light is going to escape, and it will look dimmer to us. So these variable stars are going to grow in size and shrink, and then grow and then shrink. And as they do that, their brightness is going to grow and then shrink, grow and then shrink. We can use these as a galactic measuring tape to figure out how far away objects in space are. More on that in a second. Some of them are not very regular in their repetitions of brightness. Those aren't quite as helpful. Some stars change brightness because they literally just blow up. So a supernova or a nova, which is a tiny explosion, that is obviously going to change the brightness of a star, but a supernova is only going to happen to a star once, so it's different than the pulsating variables. These are all intrinsic reasons. Something about the star itself is causing the brightness to change. But then you also have extrinsic reasons. Something outside of the star is causing it to change brightness. Or maybe it's the way that we're looking at it is causing it to change in its brightness. A good example of that is an eclipsing binary star. If you've got a very bright star and then a dim star goes in front of it, the overall brightness is going to change. The star itself didn't change, it's just that from our point of view, we're seeing more of the dim star, and it seems that the brightness goes down. Another possibility is that maybe there's a lot of sunspots on one side of the star. So as we see it, and it's rotating, we then see a side with a bunch of sunspots. Doesn't seem as bright to us, and all of a sudden we think that star's brightness has gone down. In reality, nothing happened to the star, it's just we're seeing a different side of it. That would be an extrinsic reason that we could have a star change in brightness. Here's a picture of the same star, and you can tell that in this over here on the left-hand side, it is much brighter than it is over here. This is November to September the next year, so roughly 10, 11 months or so, and the brightness of this star has completely changed. This is an example of a Cepheid variable star. As a bonus question, what telescope took this photo, and how do you know? It was Hubble, and you can tell because all of these little stars in the foreground have a little plus sign, including this star itself. If you are a star that changes your brightness regularly, a Cepheid variable star, you live in this instability strip, which we've spoken about before. You may be on the main sequence, just burning regular hydrogen, turning it into helium, but as you grow, you're going to move on the HR diagram because you're going to be brighter, and then you're going to get dimmer, and then brighter, and then dimmer. And so we put you in this, what's called an instability strip. So Cepheid variable stars are going to live in here. Just like with a light wave, the time that it takes for one thing to happen all the way around to that same thing happening again is known as the period. So maximum brightness of a star back to maximum brightness of a star is known as the period of that star. And because astronomers love to do this, you can plot that curve on a graph. When you do that, we find that it follows a very well-defined period to luminosity relationship, which means the time period that it takes to go from brightness to brightness depends on its overall luminosity. In other words, the longer it takes for a Cepheid variable star to get bright and then go to dim and back to bright again, the longer it takes, the brighter that star really truly is. The astronomer to figure all of this out was Henrietta Swan Leavitt, who worked at the Harvard Observatory with Annie Jump Cannon. And the fact that we can figure out the overall brightness of these stars based on their brightness period means that we can figure out how far away they are from planet Earth. If you saw something like this, you could obviously tell the brightness period of these stars because the time period is written right up here at the top. But if I asked you which one was the most luminous, what would you say? Which one was the brightest star? Well, remember, the longer the time period, the more luminous the star. So which of these four stars takes the longest time to go from brightness back to brightness? It's the top one. So this is the most luminous star. This one would be the least luminous because it's going the fastest. And based on how fast this goes, we can calculate the exact luminosity of that star. If you're interested in knowing the actual equation, here it is. You're not going to need to know this for a test, but there it is. Here we have a Cepheid variable star in M31 in the Andromeda galaxy. You can see that over time it's getting a little bit brighter. We are able to calculate how long it takes for that brightness period to happen. We can then calculate exactly how bright that star should be, and we compare that to how bright we see it. And that allows us to calculate the distance of this star. And if we can figure out the distance of this star in a distant galaxy, we now know how far away that galaxy is. So figuring out the fact that Cepheid variable stars and their brightness period is going to tell us the actual luminosity of that entire star allows us to figure out the distances to distant galaxies. There's not a whole lot of ways to figure out distances to galaxies other than this. There's one more with supernovas that we're going to mention. But the way that we know how far away the Andromeda galaxy is because Henrietta Swan Leavitt found this Cepheid variable star in that galaxy and was able to calculate, based on its brightness period, how bright it should have been, and therefore how far away the galaxy was. So in the easiest language that I can come up with, if you know a star's brightness period, then you know its absolute magnitude. You compare it to the apparent magnitude that we see it from here on Earth, and you can then calculate how far away it's going to be. If you can find one of these stars in a distant galaxy, you now know how far away that entire galaxy is. And you can start plotting out in 3 dimensions where galaxies are located, how far away they are from each other.